My research, got it. My research titled Quantifying in situ soil evaporation using a Model-Data Assimilation Approach. And probably you wonder why Sofia's research focused on quantifying soil evaporation. And the answer lies in the fact that soil evaporation is a major outflow in the soil-water balance in the United States Great Plains. One input of the soil-water balance is the precipitation. And here in the state of Kansas, on average, we have an annual precipitation of about 685 millimeters in a year. And 30 to 70% of that evaporation, of that precipitation, is lost due to evaporation. There are others outflow of water in the soil-water balance, like runoff and drainage, that together account for 10% of the precipitation loss. And another output of this soil-water balance is the transpiration process. But this process is linked to biomass production. So if we want to develop management practices in order to shift these non-productive evaporative losses into transpiration, first, we need a simple and a reliable method to estimate the soil evaporation. A very common method to measure soil evaporation is a traditional microlithimeter technique. So this enables us to have in situ observation of soil evaporation, and microlithimeters are pipes that are inserted into the soil, then they are excavated and bottom sealed. After the sealing, the mass of the microlithimeter is going to be recorded every 24 hours for about 2 to 3 days. So as you may think, this methodology has drawbacks like being labor intensive. That is myself trying to insert the pipe in a very dry soil condition. And it is also difficult to measure after precipitations event because everything is wet and muddy. Also, the area where we are measuring the soil evaporation is reduced. And something important to highlight is that after 4 days or even more, the soil moisture inside the microlithimeter differ from the surrounded soil. Why is that? Because the surrounded soil has roots that are uptaking water for the transpiration process. And also because with the sealing, we are interrupting the pore connectivity. And with that, the capillary rise of water is not possible. So after a certain period of time, the soil inside the microlithimeter can be drier. There are models also to estimate soil evaporation, and this model relies on soil moisture estimation. So here exists an opportunity to measure in situ soil moisture and to estimate properly the soil evaporation. With that in mind, the hypothesis of this study is that a model-data assimilation approach that combines in situ observation of surface soil moisture and green canopy cover as well will be more accurate than using just a soil evaporation model. The objective of this study is to develop and test a model-data assimilation approach that combines both a simple soil evaporation model with in situ observation of surface soil moisture using an instrumented microlithimeter and canopy cover from pictures to quantify soil evaporation rate during crops growing season and fallow periods. In this study, I ran 3 experiments. 2 of them were conducted in winter wheat in the plots of the RAIN project during winter wheat growing season 2021 and 2022, and also during growing season 2022-2023. A third experiment was conducted in bare soil conditions, also placed in ashland bottoms. Both experimental sites were close to a Kansas Mesonet station from where I obtained the weather data. The model that I implement in this study is the FAO56 dual crop coefficient that commonly is used to estimate crop evapotranspiration. Today, with this study, we are just focusing on the top 12 centimeters of the soil profile where the evaporation process occurs based on this model. So the model estimates soil evaporation by multiplying the reference evapotranspiration that in this study I download from the Kansas Mesonet, multiplying that times the reduction coefficient that is going to represent the amount of water in the soil available for the evaporation process. And I'm also going to multiply those two parameters with the difference between the maximum value of evapotranspiration, Kc max, minus Kcb, which is the basal crop coefficient. That coefficient is going to vary according to the growing season. And here we have also a graph that is basically to explain the stages of the evaporation. When we have enough water for the evaporation process, the only limiting factor is going to be the energy. That is going to depend on atmospheric conditions. So at that point, Kr coefficient is equal to 1 and evaporation is at a constant rate. When water is the limiting factor, the rate of evaporation decreases, and that is known as the falling rate stage. So, in order to measure how much water we have for the evaporation process, we measure the surface soil moisture using an instrumented microlithimeter. These instrumented microlithimeters are pipes that are inserted at the beginning of the growing season, in the case of winter wheat, and at the beginning of the experiment in bare soil. So after we insert the microlithimeter, we dig a trench in order to place a soil moisture sensor. The rods of the soil moisture sensor are going to be inside that volume. After that, we connect the soil moisture sensor to a data logger, and the data logger is going to record hourly measurement of surface soil moisture. So with that, we are recording every hour the variations in surface soil moisture. Something important to mention is that we take advantage of this setting in the 3 experiment, and we propose an approach that we call the changing storage approach. The changing storage is going to be equal to the difference between 2 consecutive observations of surface soil moisture, and that changing storage is going to be due to the evaporation. The other in situ observation that we are going to assimilate in this model-data assimilation approach is the canopy cover. To estimate the canopy cover, I collect images across the whole growing season. At the beginning of the growing season, the plants were very little, so the leaves were tiny. And at that moment, more energy can reach the soil surface. When the crops start to, and at that point, something that I forget to mention is that the canopy cover is low. When the crop grows, the leaves increase, and we are going to have the shading effect that decreases the amount of energy that is reaching the soil surface for the evaporation process. So by taking images and then analyzing the images with canopy up, we can estimate how much energy we have for the evaporation process. So across this study, we test 5 different approaches in order to predict soil evaporation. The first approach is the model alone, the dual crop coefficient alone using tabulated parameters. The second approach is a dual crop coefficient assimilating the canopy cover, how much energy we have. The third approach is a dual crop coefficient assimilating surface soil moisture. The fourth approach is a dual crop coefficient assimilating the canopy cover as well as the surface soil moisture. And the last approach is the one that I mentioned that is going to be equal to the changing storage, the difference between 2 consecutive observations of surface soil moisture. All this approach, all the predictions were tested, were validated using the traditional microlithimeter. This means that I compare the predicted evaporation with in situ measurement of soil evaporation. I went to the field and I insert the microlithimeter and I record the mass and the change in mass manually. Moving into the results, we have one-to-one plots where in the x-axis, we have the observed evaporation, and in the y-axis, we have the predicted evaporation by each of the 5 approaches for winter wheat in both growing seasons. In pink, we represent the growing season 2021-2022, and in purple circles, I represent the predictions and estimations of winter wheat growing season 2022-2023. And if we compare all the one-to-one plots, the approach that has the better performance is the dual crop coefficient, the model alone, and also the dual crop coefficient assimilating the canopy cover. And that is reflected in the root mean square error average of 0.6 millimeters per day. Here we have a time series for winter wheat growing season 2021-2022. In the first graph, we have the reference evapotranspiration for the whole growing season, starting from mid-October until mid-June. I download that reference evapotranspiration from the Kansas Mesonet, and also we have represented in bars the precipitations event that were located at the end of the growing season. And in the second plot, we have the predicted evaporation for the whole growing season by the 2 models that have the better performance. The dual crop coefficient represented with the black line, and the dual crop coefficient assimilating the canopy cover represented with the green line. And if we compare the predicted evaporation by the 2 models and the in situ observation represented with the yellow dot, that is a microlithimeter reading, there is a really good agreement in this growing season. Moving into the following growing season, last winter, again, we have the reference evapotranspiration and the precipitation events through the growing season. And if we look at the second graph, there is a pretty good agreement between the in situ observation and the predictions. There are moments where we have underestimation if we compare the predictions and the observations. Now I would like to share with you the result for the bare soil experiment that was conducted last summer. So if we look at the one-to-one lines, we can see that the better performance is provided by the changing storage approach. Here we didn't assimilate the canopy cover because we have there, so we didn't have any canopy effect. And again, we have the time series where I plot the reference evapotranspiration and the precipitations event in the first graph. And in the second graph, I plotted the predictions provided by the dual crop coefficient model alone, the dual crop coefficient assimilating surface soil moisture, represented with the pink line, and the purple line represent the predictions of the changing storage approach. And if we compare the yellow dots that are the in situ observation with the predicted evaporation, the model that results in the best estimation is the changing storage approach. So to sum up, the dual crop coefficient is a simple soil evaporation model that when it's properly parameterized, provide reliable estimation of soil evaporation. The dual crop coefficient provides more accurate estimation of soil evaporation than the Model-Data Assimilation Approach in both winter wheat growing seasons, and the changing storage approach using the instrumented microlithimeter resulted in a reasonable estimate of soil evaporation in the bare soil experiment. So here are the references, and I would like to acknowledge my advisor, my former advisor, Andres Patrignani, Gerard Klutenberg, and Eduardo Santos, that were part of my committee, my lab mates, and also the RAIN project student, and the RAIN project itself for the foundings, for the networking, the opportunity, and the people. So with that, I would like to take your questions.
Okay, great. Questions.